Okay, so we just got done doing probability, and then we talked about the binomial distribution, which was still a probability calculation, but kind of a special case where we knew there were only two possible outcomes. It was the same probability every time. We had a fixed number of trials, so there were a lot of stipulations that had to be met in order to use the binomial distribution. Today I'm actually going to talk about a couple different pieces. So the first one is just a probability density function. And that is something that we've already been looking at. It's any type of equation used to compute probabilities. So you know, on some of your homework I might have given you an equation like your P of x equals, I don't know, x squared over 10. And I gave you certain x values this worked for, and you could make a probability table for that. That was a type of probability density function. It was an equation that we used to find probability. The difference is, when we looked at it, our variables were discrete. X was 0, or 1, or 2, or 3. Now we are moving into what do we do when our variables are continuous? Because we know there are such things as continuous functions, like weight, time. Those types of things are continuous. So we can look at a function for those. It still has to be true that the area of the graph or the total probability has to add up to 1, and everything has to be positive. We can't have a negative probability. So those stipulations are still true. Since we can't list out all the values of x in a continuous function, we won't be seeing it as a table like this. We will be seeing a graph that would show us. So I want to take a look at one of these and try to draw a graph for it. So this one is a uniform distribution. Every outcome is equally likely here. We don't see uniform distributions very often because most of the time everything doesn't have the same probability, but this is a scenario when it might. So suppose that United Parcel Service is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 a.m. and 11 a.m. Let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place. So if it's at 10 a.m. on the dot, it would be x equals 0. 10:01, it would be when x is 1. 10:02, x is 2. All the way up when you hit 11 o'clock, what's your x going to be? 60. Okay. So every, we're looking at 1 minute intervals, and every value is equally likely. So he is just as likely to show up at 10:35 as he is to show up at 10:02. So if I asked you to draw a graph for this, so my x starts at 0 and it's ending at 60. We know that each of these has the same probability, right? So if I graph them, my probability is the same every single time. So what it turns out to look like is just a rectangle because of the fact that those probabilities are all equally likely. Every instance in that, we have the same probability. But the question is, what is this probability? What does my total probability have to equal? 1. So if we think about this, how long is my rectangle? 60. Okay, so I have to take my total probability of 1 and divide it between the length of my interval. 60 minus 0. It ends at 60, it started at 0. So what's the probability? 1 over 60. Okay, which kind of makes sense if we think about it. There are 60 possible outcomes, and each of them has the same probability, so 1/60th would be the probability of each specific outcome. So that is a graph of a uniform. Anytime it's just like a rectangle, that's a uniform distribution. Everything had the same probability. Let me ask you a couple questions about that. So if I want to know the probability of choosing a time between 15 and 30 minutes. So I'm saying, all right, I wasn't real precise on my graph, and you don't necessarily have to graph this. But I want the probability that you are between 15 and 30. So the probability, it's really just the area of that little rectangle. Area of a rectangle is length times width. So how long is this rectangle? 15. And we get that by doing 30 minus 15 is 15. So we're really just finding the probability is the same thing as the area. So length times width, so the length is 15. What is the height of that rectangle? 1 over 60. And we get 1/4 or 0.25. Part B. There is a 30% chance your package will arrive in the next blank minutes. Okay, so what I gave you was my probability. 30% is 0.3. We know we get that by doing length times width. Okay, I don't know how long that rectangle is, so I'm going to call it x. What is the height of my rectangle always? So divide by 1 over 60 or multiply by 60. So 0.3 times 60 is 18. So there is a 30% chance it will arrive in the next 18 minutes. But the uniform distribution isn't going to be our main focus because it just doesn't come up very often that everything has the same probability. A lot of times we see something where your probability at the beginning is kind of low and then it peaks in the middle and then it tapers off the end. We've seen graphs like this before, haven't we? What did we call these? Bell-shaped or symmetric graphs. So it turns out if something is symmetric or bell-shaped, it's what has a normal curve to it, or we can use the normal distribution. And with this, the more rectangles that you divide it into, the better your shape will get. So more rectangles will give us a smoother curve. So we'll find that the more data we have, the more likely it will be to turn out to be a normal distribution. When you are looking at a normal distribution or a bell curve, what did this peak represent? Do you guys remember? We even saw that when we talked about it. It was the mean. All right, and then we know, like from the empirical rule, then you can measure out so many standard deviations from there. So in this, the center, your peak, is the mean. Then when our graph kind of starts to switch directions, those will be marked. You don't have to pick those out yourself. But that is the standard deviation, that distance from the center out to that point. So we'll be talking about the normal distribution pretty much all week. We will find a few things about it, some characteristics. It's symmetric across the mean. You have about the same number of points higher than the mean as you do points lower than the mean. Since it's symmetric, you have a nice peak in the middle. The mean, median, and mode are all the same. We kind of talked about that with our bell-shaped data before. If it was true bell-shaped data, the mean and median turned out to be the same. And that highest point is then our mean. We can look at our inflection points, which we'll talk a little more about. It's just how far it is to get to one standard deviation. Since we're talking about probability, the area under the curve is 1. So this area under the curve is representing the probability. Since it's symmetric, That means there's a 50% chance you are above it or a 50% chance you are below your mean. The empirical rule is still true with bell-shaped data, so I did put that slide on there. We've seen it before. It's on our formula sheet. But remember, empirical rule told us that you had 68% of the data within 1 standard deviation, 95% within 2, and 99.7 within 3. So this bell-shaped data isn't new to us. We've seen it a lot, but I'm giving it a new name. And it is the normal distribution. So let's look at this one. And I apologize, I know it's kind of dark. I was stealing graphs from your textbook. So is this a normal distribution? Yes. How would I know it's a normal distribution?
Standard deviations are equal.
You're looking for bell-shaped. If I gave you this one, would it be normal? No, because it's skewed left. If I gave you this one, is that normal? No, it's skewed right. So if it's normal, it's nice, symmetric, bell-shaped data. I said right and left backwards, didn't I? But you knew what I meant. Can you tell me what the mean is on this one? 2. That's the peak. Okay, standard deviation. So the standard deviation is how far it is to get from here to here. 3. And that should be the same distance from here to here, and it is. So my standard deviation is 3. Any issues with that one? Finding the mean standard deviation? So I'm going to put another graph up here. It has 2 different functions, A and B. Both of these have a mean of 10, which we can see they both peak at 10. But one of them has a standard deviation of 3. The other has a standard deviation of 2. I want to know which one is which. So one of these standard deviation is 3. So how would you tell from a graph what the standard deviation is?
If it's a longer standard deviation, it's wider.
Right. The higher your standard deviation, the more spread out it's going to be. So my bigger standard deviation is 3, so which graph is more spread out? B. It's a wider graph. And then that means A has to have a standard deviation of 2. So the smaller standard deviation makes a narrower curve. So far, so good? Okay, this slide, you might put a star next to it. So there's a couple different ways we can interpret the area under the normal curve. And some of your homework, I'm going to say, write the 2 ways you can interpret this. It'll probably show up on test or quiz. You can think of it as a proportion or a probability. So if I said 30% of my class was tired this morning, okay? I could think of it as the proportion, so I would expect 30% of you guys to be tired. Or I could think of it as a probability. The probability that Eli is tired is 30%. So a proportion is kind of like if you're talking about a whole group, or a probability for a specific person, and we can interpret it either way. So the last example for section 1. The weights of giraffes are approximately normally distributed with a mean of 2,200 pounds and a standard deviation of 200 pounds. Draw a normal curve with the parameters labeled. So what I'm expecting when you draw the curve. A normal curve, so we're looking for a bell-shaped curve. Okay, as close as you can get. My parameters, I'm wanting you to basically label your mean and the first standard deviation. So my mean is 2,200. All right, if the standard deviation is 200, then what is this value down here? You have to do your mean minus 200, and then this one would be your mean plus 200. So that's part A. I ask you to draw the graph. Part B. I want you to shade the area under the normal curve to the left of 2,100 pounds. So 2,100 would be halfway in between those. And I'm asking you to shade everything less than that, everything to the left. Tomorrow we will be looking at some graphs with things shaded like this and finding those probabilities. Part C. Suppose that I told you the area to the left is 0.3085. So if I told you that this shaded portion is 0.3085, I want two interpretations. So I'm basically asking you for two sentences. I told you that you can interpret the area as a proportion or a probability. So the proportion is of the entire population. So I could say the proportion, my population here is giraffes. So the proportion of giraffes with a weight, I shaded everything less than 2,100. So I could say, oops, less than 2,100 pounds is 0.3085. So if I looked at every giraffe, almost 31% of them weigh less than 2,100 pounds. The second interpretation is as a probability. So if I pick one particular giraffe out, the probability that they weigh less than 2,100 pounds is 0.3085. So that's my two interpretations. I can think of it as a proportion of the whole population or the probability of one giraffe. Questions there? I'm going to go ahead and give you some time to work. I might take a few minutes at the end and kind of talk about just a couple pieces from the next section. But I think I want to stop first and let you work on the homework for this. It's actually really important. And it really makes life a lot easier because we can easily calculate probabilities for things that follow the normal distribution. When we look at this, remember finding z-values before, like back in the first unit? We found z-scores, and the whole purpose of that was to basically put things in a common unit. So, you know, if you had this score on a history test and this score on a math test, how do those compare to each other? And we looked at a z-score really told us how far it was from the mean, how far above or below average. So a positive z-score meant you were above average, a negative meant you were below average. And so some of our examples, like we looked at, you know, we would take a man and a woman and compare their heights, and we wanted to know who was relatively taller. And you had to compare the woman to other women and the man to other men and see who was taller in comparison. So with this, we can take any normal distribution change to z's, find our z-scores, and use a probability table. And you actually have this probability table already. So in this notes packet that we've been using, if you flip through, so I think it's in, hopefully I copied it for you. Yeah, you've got the normal distribution. Was it the third piece of paper on there? Table 5 says standard normal distribution. It has a picture up at the top of a graph, a bell curve, and in that it has something like this, and it has it shaded. So what it's telling you is you have to find the z-score, and then the probability that you look at in your table is what's shaded up in that picture. It's everything to the left, so everything less than that. So you'll notice like the very bottom corner is almost a 1, because if you're all the way out here, you would have almost 100% of the values below that. So this table gives us everything less than what we are looking at. So we will do maybe just one example, and then we'll pick up with this tomorrow, just practicing these probabilities. So IQ scores can be modeled by a normal distribution with a mean of 100 and standard deviation of 15. Find the area to the left of a score of 120. All right, so 120 is my x. If I am going to use this table, I can't have x though. What do I have to have? Z. So we know how to find z's. We did it way back when, so it's on your formula packet under chapter 3, the sample z-scores. It's also again right under chapter 7. They have it listed again. So our z is x minus mu over sigma. So my x is 120 minus the mean is 100 over 15. When you get these z-scores, go to 2 decimal places. That's all the table allows. So make sure you are rounding up when necessary. So I get a z value of 1.33. So when we looked at this before, we would have said you're 1.3 standard deviations above average. But we didn't really put that into any context. What I'm asking you now is, okay, you're up here, what's the probability, or the area to the left? So the probability that you're less than that. So here's my z. So we just have to find that number in our table. The table gives us everything to the left. So when you use this table, it takes a little getting used to. On the left, it starts out with negatives. It gives you the first decimal place. So you have to go down to the 1.3 row. And then we go over to the 0.03. So we'll go over 4 numbers, and it gives us 0.9082. I want to make sure we all know how to read this table. So let me show you real quick. All right, so you go, we want 1.33, so we go down to 1.3. Then if you look at your columns, this is the 0.00, 01, 02, 03. So we're in this column. So I have 0.9082. Does everybody see that? Okay. So my table gives me area to the left. What if I wanted the area to the right?
1.
Yes. So the nice thing about this If you forget that it's area to the left, when you are looking at your table, the picture shows you. This is what area it's giving me. So if I want the other, we have to do 1 minus that.